The second speaker, our second speaker in the second half of the session is Carlos Cinelli from University of Washington. Carlos just obtained his PhD from the Department of Statistics of UCLA. He just started in the Department of Statistics at the University of Washington as assistant professor. His research focus is causal inference and statistical methods for transparent and robust causal claims in empirical sciences. So Carlos, please take it away.
Okay, great. So hi, everyone. Thank you for inviting me. It's a great pleasure to be here. So I'm Carlos Cinelli, incoming assistant professor at the University of Washington. And this is joint work with Chad Hazlett from UCLA. And in this talk, I'm gonna present you an omitted variable bias framework for sensitivity analysis of instrumental variables. And to make things concrete, I always like to start with an empirical example. And here we're going to use a classical example from economics. And our research question here is, what is the effect of an extra year of education on someone's earnings? And a first approach to this question, the most natural approach for applied researchers, is to run an ordinarily squares regression on log earnings Y on our treatment education D, adjusting for some observed covariates X, such as race, experience, regional factors, and others. And here we're going to reproduce the results of a famous paper from David Card. And this is what we get if we run this regression. So we find a positive association, of course, between education and earnings. And we find that that each year of education approximately is associated with an increase of 7.5% in earnings. But the problem with this regression, as everyone will question, is that many important variables that affect both schooling and earnings are not included in X, such as family wealth or ability. So we have unmeasured confounders here. Thus, our restricted OLS estimate, that's why I put this RES here for restricted, and this notation I'm gonna use also for the IV estimates. So our restricted OLS estimate is not reflecting the true causal effect and may suffer from what is known as omitted variable bias or unmeasured confounding. So what can we do now? And I'm going to repeat some of the presentations that I already discussed IV, or Mendelian randomization, which is IV in genetics. So that's where instrumental variables comes in. So if we can find a variable Z, first, this Z needs to change the incentives of our treatment D, in this case, schooling. So we need to find a variable Z that change the incentives to get more or less education. And second, and most importantly, this Z, this instrument must be otherwise unrelated to earnings, to our outcome Y. And what this otherwise unrelated means is that Z must be associated with the outcome Y only through its association with the treatment D, with schooling. So if we can find this variable, this instrumental variable, we're going to call it the Z, then we can obtain a valid estimate of the causal effect of schooling on earnings, even without measuring all these unobserved confounders U here represented by a bidirected edge. Now, I'm putting a caveat here is that this is not a non-parametric claim. So IV requires other parametric assumptions, which I'm not going to discuss here. This does not change the algebra of the sensitivity analysis that I'm going to show you. It only changes the interpretation, whether your target is an average causal effect or a local average treatment effect, or so on. But we need that to use Z as an instrument to recover some causal effect. And here I'm omitting the observed variables X just for simplicity. So this is what the usual instrument looks like. And Card, in our example, argued that the presence of a nearby college could be a valid Z, a valid instrument. So we're going to call this variable proximity. And he argued that because of reasons. First, that students who grew up far or closer to college, so for example, here, students who grew up far from college face higher costs of education. So if you're far from college, this may affect your decision whether you're going to study more years or less years of education, because it makes going to college more expensive. Or conversely, if it's closer to college, it makes it less expensive to attend college. And second, and most importantly, so this is the relevance condition, right? But the most important part here is part number 2. The Card argues that proximity to college is not itself confounded with earnings, meaning that there are no measured confounders of proximity to college and earnings. And also that proximity to college only affects earnings through its effect on your decision to take less or more years of education. So if these assumptions hold, and that's a big if in this example and in many IV examples, we could use IV regression, adjusting for X, for the observed course X, which I'm not showing here for simplicity, to estimate the true returns to schooling. And in this case, we'll obtain a value of 13.2%. I'm going to explain to you how we get this next. We also saw in other presentations too, right? But the main problem here is that proximity to college is not randomized. So you're not flipping a coin to decide whether someone lives nearby a college or not. So couldn't we have the same problem that we had with ordinary least squares with IV? And the answer is yes. And in general, there are two main threats to the IV to the validity of an IV estimate. So the first one, what we just said, is that the instrument may not be quote unquote as good as random, and there may be confounders of the instrument outcome relationship, such as W1 in this DAG here. So this is violating what people usually call the ignorability of the instrument assumption or the unconfoundedness of the instrument assumption. But second, even if the instrument is random, such as in a randomized controlled trial, if you have any random incentive or a random assignment to treatment, our instrument may have side effects, such as a variable W2 here, that affects our outcome other than through its effect on the treatment. So that's also a violation of the IV assumptions. And this is also called the exclusion, usually called the exclusion restriction. Now, in early econometrics works, they used to conflate these two assumptions and called everything exclusion restriction. But here we're making this distinction just for, because it's easier to think about whether something is a confounder or if something is a side effect, to reason about the processes of how the IV can be violated. And this is indeed the case in Card's example. We can think of several variables that satisfy that could be playing the role of these violations. So for instance, family wealth or simply better regional indicators are likely confounders of proximity to college, but we did not measure them in the survey that Card is using for this study. So although we propose IV as a solution to the omitted variable bias problem, our IV estimate itself may suffer from omitted variable bias. So how much can we really trust this 13.2% estimate? So to give a precise algebraic answer to this question, bear with me for a couple slides. I want to review the two main approaches to IV estimation and show to you how they're just different flavors of ordinary least squares estimation. And then we're going to go back to the sensitivity. So let's start with indirect least squares and two-stage least squares. And these are probably the most widely used estimators for IV. So starting with indirect least squares, we have two regressions, two auxiliary regressions. So the first one is usually called the first stage. And the first stage is trying to capture the effect of the instrument on the treatment. And here we find that those that grew up near a college had in fact an extra 0.3 extra years of education. So indeed, growing up near a college is changing the incentives to treatment, to get the treatment here, which is education. And the reduced form is aiming to capture the effect of the instrument on the outcome. So if you're coming from a randomized controlled trial literature, this regression here is usually called the intent to, so this estimate here used to call the intent to treat effect or the intent to treat analysis. For example, if you have non-compliance, so you have a randomized treatment and the actual treatment. Assignment to treatment and actual treatment. And here in our example, we indeed find that those that grew up near a college had in fact 4.2% higher earnings. Now to get the IV estimate itself, because we are interested not in the effect of Z, but in the effect of D, we simply take the ratio of these two regression coefficients, and that's what gives us the 13.2% that I showed you before. And inference can be done in this framework using the delta method for getting the confidence interval of a ratio. Now, a closely related approach, and actually numerically identical approach, even though we're going to do something different, is called the two-stage least squares. So here we're going to take the results of the first stage, the predictions of our treatment given the instrument, and we're going to call this D hat, and now we're going to regress our outcome on D hat. And the coefficient attached to D hat here is our two-stage least squares estimate. And it turns out here that it's numerically identical to the indirect least squares estimate. And inference also is numerically identical. So the standard errors is also going to be numerically identical to the delta method in the two-stage least squares approach. Now, another approach for IV estimation is the Anderson-Rubin approach, which is numerically identical with Fieller's approach for the confidence interval of a ratio in this just identified case. So here we're going to do something a little different. We're going to start by guessing what the true causal effect is. We're going to say that the true causal effect of D on Y is some specific value, say tau naught. Then we're going to create this untreated, putative, untreated potential outcome where we subtract from Y the causal effect of D, given this true causal effect tau naught. And then we regress this new variable on the instrument and the covariates. Now, the important thing to know here is that if Y is only related to the instrument because of its effect on the treatment, because the instrument affects the treatment, then this new variable, this Y tau naught, should be unrelated to our instrument Z, right? Of course, bearing sampling variation. So this phi should be equal to 0. And that's the logic that the Anderson-Rubin regression is going to exploit. So for the point estimate, we are defining here the Anderson-Rubin point estimate as exactly the value of tau naught, such that brings this phi hat equal to 0. And again, this is numerically identical to all other two IV estimators. It's just the ratio of the reduced form by the first stage, and it gives us 13.2%. But for the confidence interval, we do something a little different. What we do is we collect all values of tau naught such that we do not reject the null hypothesis that phi is equal to 0. And that gives us this confidence interval. And there are two important facts for our purposes here. There are two important facts that that we should know about this confidence interval in this Anderson-Rubin approach. The first one is that the confidence interval will include 0 if and only if we cannot reject the null hypothesis that the reduced form is equal to 0. And the second property of this confidence interval is that this confidence interval will be unbounded if and only if we cannot reject that the first stage is equal to 0. And this approach has correct test size regardless of instrument strength. Okay, so these are the regressions we have. So we have the first stage, reduced form, and this Anderson-Rubin regression. And these are the adjusting for X. And these are regressions that gives us the 13.2%. But these are not the regressions we want, because these regressions are only adjusting for the observed covariate X, and to account both for violations of the exclusion restriction and violations of the unconfoundedness of the instrument, we would need to further adjust for an observed covariance W. So the main question we would like to answer here is how would including W in our V regressions change our inference? So since for LS for the sensitivity of IV, and that's what we're going to do here. We're going to build upon these results of this GRSSB paper, also with Chad Hazlett, making sense of sensitivity, extending omitted variable bias. And we're going to extend these tools to the IV case. So that's what we're going to see now. So how can we do it? So I guess the first thing that we should ask ourselves is what can we learn about the sensitivity of the IV estimate from the sensitivity of the reduced form and first stage themselves? Because, for example, in economics, in econometrics, people always tell applied researchers to look at the first stage and look at the reduced form and see whether they make sense and are coherent with the causal story they have behind the data. But beyond that, if we look at these regressions by themselves, what can we tell about the sensitivity of the IV? And it turns out we can tell a lot. So as we have just seen, all IV estimators are of this form of the reduced form divided by the first stage. And the simple algebraic fact already gives us two important lessons about the sensitivity of the IV. And the first one is that if you're interested in assessing the null hypothesis of zero causal effect of your IV estimate, then all that matters is the sensitivity of the reduced form regression. And that's it. So if you want to perform sensitivity analysis against the zero null hypothesis, all you need to do is run the reduced form regression, regress your instrument against your outcome, and do vanilla OLS sensitivity analysis on a reduced form. Now, the other thing we can see here is that if I take this denominator and if I can bring it arbitrarily close to 0, either from the left or from the right, I can make this IV estimate arbitrarily large. So what we're saying here is that if you cannot rule out omitted variables that are strong enough to change the sign of the first stage, then we can also not rule out omitted variables that are strong enough to make the IV estimate basically informative about the magnitude of the causal effect, right? So if you're interested not only in the null hypothesis of 0, but 0 and values arbitrarily worse than 0, then you should also check the sensitivity of the first stage. So what I'm telling to you here, so if there is only one thing that you remember from this talk, is that if you want to do sensitivity of the 0 null hypothesis, you can just do sensitivity on your reduced form. And what I'm telling to you, what I'm telling right now about the sensitivity of the IV, for the point estimate, it holds for all estimators we have discussed here, for all 4 estimators. And for confidence interval, this formally holds for the Anderson-Rubin Fieller approach. These 2 lessons, let's say, that we draw. So, okay, so I told you that we can learn a lot about the sensitivity of the IV just performing sensitivity analysis of the reduced form and first stage regressions. But how can we do sensitivity analysis of the reduced form or the first stage or any OLS estimate? So that would require another 30 minutes presentation. So here we're gonna just see a crash course because the basic things are easy to understand. And I'm gonna use the reduced form as the example. So we're gonna start by characterizing the violations of the IV assumptions, the violations of the IV assumptions with 2 sensitivity parameters, which parameterize the strength of the omitted variables W. So the first sensitivity parameter is saying how much residual variation confounders or side effects of the instrument explain of the instrument. And the second sensitivity parameter is parameterizing how much residual variation this omitted variable W explains of the outcome. And once we have these 2 sensitivity parameters, that's all we need to know to compute the worst possible inferences we could have given a postulated strength of W. And this is actually very easy to compute. The only thing you need to do is when you're constructing your confidence interval, you're going to replace the traditional critical value, for example, 1.96, if you're using a 95% confidence interval, with what we're calling an adjusted critical value. I'm calling this T dagger. And this T dagger is a function.
It's very easy. Then we get it.
Did someone ask something? Okay, I think I heard something. Okay, never mind. So we're going to replace the traditional critical value of 1.96 with this adjusted critical value that is a function of these 2 sensitivity parameters. It's also very easy to compute. And then you just take your estimate, multiply the error by this new critical threshold, subtract sum, and then you're going to have a confidence interval that takes into account both sampling uncertainty and systematic biases due to these omitted variables. Now, another exercise we can do is the inverse question of what we just did here. So here we are saying, give me what you think, tell me what you think, what the strength of confounding is, confounding or pleiotropy, for example, in MR, or a violation of the exclusion restriction. Sometimes I say confounding, but W could be mediators, right? So in this here, I'm saying, tell me the strength of W, and then I'm going to give you all the inferences compatible with that strength of W. But we could ask the inverse question, which is probably very informative for the reader, which is, what is the value of W that breaks down my inference? So we're going to ask, what is the minimum strength of W needed to be problematic, to bring this so that some value is included in this confidence interval. For example, the 0 effect is included in the confidence interval, if 0 is the null hypothesis that I care about. And we have 2 main statistics for computing that. The first one is the robustness value, and the second one is the extreme robustness value. And they're going to characterize this minimal strength of the unobserved variables W. I'm going to explain to you what they mean in the example, because I think it's easier to explain in the example directly. So for now, I'm just going to say that they exist and they characterize this minimal strength. And then the third thing that we can do in the sensitivity analysis for OLS is to compute formal bounds on the strength of the omitted variables, W, if they were as strong as the observed covariates X. And why would we want to do that? This can help us leverage claims of relative importance of variables. So for instance, if we know that certain observed covariate X should be one of the most important determinants of the instrument variation, then we can use that to put plausible bounds on the strength of W, because W should be weaker, for example, than X, or the same strength as X. And vice versa. We're going to see this example is actually not going to be robust. Okay, so this is how we perform sensitivity analysis, the crash course on sensitivity analysis for OLS. And how can we do that for the IV estimate itself within the Anderson-Rubin framework? That's actually pretty easy to do. So for example, if we want to perform sensitivity for a specific null hypothesis, we're going to take our tau naught and create the putative potential outcome where we subtract Y from tau naught. Then we run our traditional Anderson-Rubin regression, regressing Z on tau naught. And then the trick here is just noticing that sensitivity analysis for the null hypothesis that phi is equal to 0 is exactly the sensitivity analysis for the null hypothesis that causal effect is equal to tau naught. The only difference now is that the sensitivity parameters will have a different meaning. Well, actually, the first sensitivity parameter is the same as how much residual variation W explains of the instrument. But now the second sensitivity parameter is going to be how much residual variation W explains of Y sub tau naught. And under certain causal assumptions, this Y sub tau naught is the untreated potential outcome, for example. Okay, so this is the sensitivity analysis for a specific null hypothesis, but we can also actually recover all possible inferences given any strength of W. And to do that is also super easy. You can do that with any software that compute Anderson-Rubin confidence intervals. We're going to just replace the traditional critical threshold of 1.96, for example, with the OVB adjusted threshold. And then you can just invert this test and recover all values of tau naught compatible with omitted variables as strong as the R square, the sensitivity parameters. So with this, we can get all usual OLS sensitivity results for IV estimates, and we can define and compute robustness values for IV. We can create contour plots that I'm going to show you next, and so on. Okay, so now let's go back to our running example and see these tools in practice. Excuse me. So I'm going to start with the sensitivity analysis of the reduced form regression. Okay, so the reduced form, remember, is the regression of the instrument on the outcome. And why am I gonna do that? Because the sensitivity of the reduced form is exactly the sensitivity of the IV when you're interested in the null hypothesis of zero effect. So if I cannot rule out that the omitted variables can bring this reduced form to 0, I cannot rule out that these omitted variables can also bring my causal effect estimate to 0. So here, just to illustrate this, so this is the minimal sensitivity reporting that we are proposing. So here we have the original estimate, the original standard error, then original t-value. So these are all in the ideal world where our instrument is perfect. And now here I'm going to ask you to just compute 2 new sensitivity statistics that characterize the robustness of this estimate to violations of the traditional assumption. So we're going to start with the robustness value. Okay. So what is this robustness value of 0.67% telling us? So it's telling us if confounders or side effects explained 0.67% both of the residual variation of the outcome and of the instrument, these confounders or side effects would be sufficient to explain away the reduced form estimate and hence the IV estimate at the significance level here that we chose 5%. Okay. So this is the robustness value. And now we have another sensitivity statistics, the extreme robustness value. And what this 0.05% is telling us is that if we are not willing to constrain the strength of association of the omitted variable with the outcome, So we can leave that completely unconstrained. I don't want to say anything about how W is related to the outcome. Then these omitted variables, side effects, or confounders would need to explain only 0.05% of the residual variation of the instrument in order to be problematic, okay? But now it comes a hard question. Are these numbers big or small? Sometimes it's hard to judge. So to put these numbers in context, to help the researcher put this number in context, we provide here the bound on the strength of W if it were as strong as one observed covariate we have here, which is a regional indicator of whether the individual lived in a metropolitan area. So if W were as strong as this SMSA variable of the metropolitan area, dummy, then it could explain 2% of the outcome, and it could explain 0.6% of the instrument. So this implies an OVB adjusted critical value of 2.55. So now if we check our original T value, and we see that it's lower than the new critical threshold, right? So the critical threshold is now 1.96. It's larger now because we're considering systematic biases. So we conclude that omitted variables as strong as SMSA would be sufficient to explain away our estimate, okay? So this is the sensitivity of the reduced form, and it already tells us a lot about the sensitivity of the IV estimate, but we may be interested in checking the whole range of sensitivity of the IV with different postulated strengths of the violations and different bounds. And to do that, I think the best plot. So in the left side, we have the sensitivity contours of the lower limit of the confidence interval. And in the right side, we have the sensitivity contours of the upper limit of the confidence interval. So let me explain to you the sensitivity contour of the lower limit. So here in the x-axis, we have how strong the omitted variables are associated with the instrument. And the y-axis, we have how strong the omitted variables are associated with the untreated potential outcome. And so these two axes are parametrized, again, in terms of residual variation explained, or partial R squares. So here in the lower corner, we have the original lower limit of the Anderson-Rubin confidence interval, which is 2.5%. And as we move along the diagonal, we are postulating omitted variables with increasing strength. So it eventually brings the lower limit to 0, or it makes the lower limit unbounded, okay? And these red diamonds are showing you bounds, positing bounds on the maximum strength of omitted variables if it were as strong as the regional indicator, SMSA, or an indicator of race. And in the right-hand side, we have the same thing, but for the upper limit of the confidence interval. So for example, in this plot, we can already see, for instance, that if we cannot rule out residual confounding, for instance, as strong as this regional indicator for whether you lived in the metropolitan area, then we could not rule out anything between -2% and 40% of the true returns to schooling, which in this case is pretty uninformative. But so this is a case where the sensitivity is not very, let's say, positive, but there are examples where estimates are more robust to residual estimates. I'm going to show you a paper that you can read later for a more positive example. Okay, so that's it. These are the main tools, let's say. So just to conclude, most instrumental variables, and here I'm including all instrumental variables, including median randomization, okay? So are not really random. For example, in median randomization, we can have population structure, linkage disequilibrium, and other problems. And also they could affect the outcome other than through its effect on the treatment. So we can have violations of the exclusion restriction, and median randomization, they call this pleiotropy, for instance. So IV can also suffer from omitted variable bias, and the bias can turn out to be worse than vanilla ordinarily square. So we should assess the sensitivity of our IV estimates. But the good news here is that assessing the sensitivity of an IV estimate is as easy as assessing the sensitivity of an LS estimate. So for the zero null hypothesis, I just showed you the sensitivity of the IV reduces to the sensitivity of the reduced form. That's it. You can do that today in your paper using our software SenseMaker, for instance. And then for the general sensitivity of IV, we can easily explore how postulated confounding or side effects change point estimates, lower and upper limits of confidence intervals, compute robustness values and bounds very easily within the Anderson-Rubin framework. And all these things like the sensitivity of the reduced form, the first stage, or for a specific null hypothesis, you can already do that with current software that we have, SenseMaker. And we have full-fledged software for IV sensitivity coming soon, both for R and Stata. So if you want to learn more, please check out the papers. So this paper is, and I'm talking, is this working paper called An Omitted Variable Bias Framework for Sensitivity Analysis of Instrumental Variables. I also have a paper applying this to Mendelian randomization specifically. There you can actually see a more robust example that survives some of the sensitivity analysis that we perform. I also suggest, if you've never seen these sensitivity tools for OLS before, reading the JRSSB paper, Making Sense of Sensitivity Extended Omitted Variable Bias. And the software is this one here, SenseMaker. We also have a paper explaining how to use the software in case you need more worked out examples. So that's it. Thank you. I hope I was okay on time.
Yeah, we can take one quick question.
So can I ask the questions, Carlos?
Yes.
Can you extend those approach to a nonlinear model?
We're currently working on that. So just to clarify, we don't need the assumption of linearity itself, in the sense that, for example, the IV estimand, this ratio of the two regression coefficients, can have a causal interpretation even if we don't have a strict linear structure equation, right? But we are constraining ourselves to the sensitivity of the IV estimand, which is the ratio of these two OLS coefficients. We are trying to extend this to GLMs, like logistic regression or probit or whatever. But it turns out the algebra is not like as clean as for OLS. But so far, no. So far, this is for ordinary least squares, and we are trying to see whether something similar can be done for generalized linear models. Okay. But note that we don't impose any constraints on the omitted variables. So they could be nonlinear transformations of like W square, whatever, right? Like. Okay. As long as you can express it linearly, but it could be nonlinear transformations, right? Like, I'm
okay.
Not sure
thank
if
you,
I answered
Carlos.
the question.
Oh, sorry.
All right, thank you.
So, thank you for your talk.